Hello everyone. Let us now discuss the analog signal reconstruction, because once the signal is sampled using the sampling process, it is fed to the digital signal processor. DSP chip performs some algorithm or some functionality inside it, and the output of the DSP chip will be a digital output that can be represented by YN. And graphically, if we see that this YN is actually the series of impulses, and these impulses are spaced at a span of capital T sampling period, capital T time, which is also known as the sampling period. Now once this stream of impulses is applied to the D to A converter, the D to A converter involves the holding operation. Therefore the value, every value will be held for a capital T time. So at the output of the D to A converter, we get actually a staircase voltage, staircase shape voltage, and we represent this as y hat t. Once this y hat t is applied to the low pass filter, it gives the reconstruction filter. It is known as the reconstruction filter, and the output will be yt. And if we will use an optimum filter here, then we will be able to perform the perfect reconstruction, and we will see how what type of filter we will use here. Now, to do the analysis further, let us consider only one pulse, and then we will carry forward the effect of one pulse to the other pulses also. Okay. So the impulse response of this pulse is given by ht equal to 1 for 0 to capital T, and time going from 0 to capital T, and 0 otherwise. So this is the representation of the pulse with this function. If we take the Fourier frequency response of this system, of this pulse, that means we take the Fourier transform, we get ht e to the power minus j capital omega t dt. Since ht will be 1 from 0 to capital T, so we change the limits here. We solve it further, right? We reach up to this point where it will be 1 over minus j capital omega e to the power minus j capital omega capital T minus 1. You extract e to the power minus j capital omega by 2 out, right? So you will be reaching to this equation. You then multiply and divide by capital T by 2, and you can use the Euler's identity, and this will be equal to sine of capital omega t by 2 and divided by capital omega t by 2 with a scaling factor of t by 2, so that the resultant equation remains the same as the previous equation. Okay. Now, if we now this is the frequency response of the pulse, right? Then what is the magnitude? If we plot the magnitude response, this is actually a sine x by x pulse. All right. This is sine of capital omega capital T by 2 and capital omega t by. This is of the form sine x by x. Now, if you plot the magnitude response, once you take the modulus, everything will be above the x-axis, and at 2 pi by 7, 2 pi minus 2 pi by 7, you will see that there will be it's a kind of sinusoidal waveform, where nothing will be there on the negative side, because we are plotting the magnitude response. And since the magnitude response is an even function, whatever is there on the right side of the imaginary axis will be exactly the same as on the negative side of the imaginary axis. Now, in the case of an ideal, we consider one pulse. We consider the output of the D to A converter as the staircase voltage. But in the case of an ideal D to A converter, the waveform will be, instead of square pulses, we will have the impulses here. So once the impulses are applied to the filter, this is the ideal low pass filter, right? With response given like this. Now, if we apply these impulses to this filter, the output will be yt. And let us see what should be the how it should behave further. Now, if we apply the signal y hat t, so we apply this signal y hat t. In the ideal case, as I said, we will take impulses, and this is our filter. Now, if we apply, so our yt will be at the output, and y hat t will be convolved with this h capital omega. That means ht is the time domain time domain impulse response of the filter. So yt will be equal to the convolution of ht and y hat t. So what is ht? We already saw that if we take the ht as sine of pi t, capital T divided by this, and this has to be convolved with y hat t. What is y hat t? Y hat t is yn convolution with these impulses, right? So if we do it like this, so this signal, this function sine pi t capital T divided by pi t capital T, uh, we take inside the sigma, and we know that once a function is multiplied by an impulse function, delayed version of the impulses, then the function itself gets delayed by the same amount. So that's what we do. This delta function is being convolved with the sine function. So sine function will itself be get delayed by n capital T. So that's what we get here, right? Yn into sine of this part, and the same part will be divided by will come in the denominator also. Now the original signal can be obtained by adding together an infinite number of sin x by x pulses. From where the infinite number of sin x by x pulses will come? Because we considered only one pulse. This is this sin x by x function. The sin x by x kind of response is only for the one pulse. But if we consider infinite number of pulses, so therefore at the so therefore the original signal can be obtained by adding together an infinite number of sin x by x pulses. The nth pulse is shifted through a distance n capital T with respect to the origin and multiplied by a factor yn. That's what we get here. So nth pulse will be shifted by n capital T and multiplied by this factor yn. Now this recovery process is called interpolation, and we will see that. So this is the sync function. This is the sync pulse at n equal to 0. This is the sync pulse at n equal to 1, 2, and so on. So there will be infinite number of sync pulses. So once you start joining the top of these sync pulses, you will see the end. You will basically you will interpolate the signal. So that means you use the envelope of this envelope of these sync functions by joining the top of these pulses. So you will be able to recover the original signal back, which is your yx, and which is basically xt signal, right? Now the signal xt is reconstructed from the samples of xn by summation of weighted and shifted sin x by x pulses. Now this was about the reconstruction. This is how, so that means how can we perfectly reconstruct the signal waveform if we pass the D2A converter output from a filter which is the ideal low pass filter, and the response of the filter has to be sine pi t by, basically it is a sync function. So if it is a sync function filter, then we can recover the signal back perfectly. So therefore for a perfect reconstruction, the filter has to be a sync function. All right, then let us see some more signals where I will try to introduce unit impulse function. We have already seen this function, but let us see the actual definition of this unit impulse function. So unit impulse function is delta t is basically equal to infinity. So here is an arrow at the y-axis. You will see that the arrow is pointing towards plus infinity, and we say that delta t is equal to infinity at t equal to 0, and it is 0 at any other point. But if we take the area under the curve, that means if we take the integral from minus infinity to infinity, delta t dt, this has to be 1. So that's how actually the impulse function should be defined. And we can also understand by, let's say this is a pulse. The length of this pulse is epsilon, for example, and the width is 1 over epsilon. So the multiplication, the area of this rectangle will be 1. Now you reduce the length of the rectangle, so you will have to increase the width of the rectangle so that the area remains the same. And this is true for any shape of the graph, right? If this is a triangle, then if you reduce the length of this length of the triangle, so you will have to increase the height of the triangle so that the area under the curve remains the same. So so this is an even function, right? For any even function, this is true. So we can say that limit epsilon approaches 0 if the width of the even function approaches 0, then this limit of any even function will approach to delta function. So this is the actual definition of the unit impulse function in the time domain. Now let's look at more signals. Real exponential signal. The continuous time complex exponential signal is of the form xt equal to c of e to the power at, where c and a are in general complex numbers. Depending on the values of these parameters, the complex exponential can exhibit several different characteristics. Now, if a is growing, if a is greater than 0, it is a growing exponential. If a is less than 0, it is a decaying exponential, right? Now, let's look at the complex exponential signal, where the uh, in the previous case it was the real exponential signal. All right, now let us take the case of a complex exponential signal where your c and a both complex numbers. Now if we this is the case for the real exponential signal. Now we see that this is the case for the complex exponential signal. Now this is c is equal to, because if c is expressed in the polar form, it will be mod c e to the power j theta. All right, and a in rectangular form, it will also be let us say it is expressed in the rectangular form, then c of eat is mod c e to the power j theta and e to the power r plus j omega 0 t. And we can further solve this and we will reach to this equation. Thus but if we see that for r equal to 0, the real and imaginary parts of a complex exponential are sinusoidal, because when r becomes 0, this factor will go to 1. Similarly, for this factor, when r is 0, this factor will go to 1, and the two terms become sinusoidal. Complex exponential are sinusoidal. Now, when r is greater than 0, sinusoidal signals multiplied. So, when r is 0, these will become pure sinusoids. When r is greater than 0, sinusoidal signals will be multiplied by a growing exponential like this. And when r is less than 0, sinusoidal signals will be multiplied by a decaying exponential like this. Clear? Then in the discrete domain also we can represent the function xn equal to c of alpha c into alpha to the power n. If c and alpha are real, and if mod alpha is greater than 1, the magnitude of the signal grows exponentially. If mod alpha is less than 1, it grows, we have decaying exponential. So this is for the case of discrete signal. Exactly the same graph is shown once again. So this is the unit impulse function, and if this is the unit impulse function, the frequency response of the frequency response of the delta function is a flat response. All right, we will discuss these things in detail once we will do the Fourier transform and all. The impulse function delta t is a signal of unit area, right? And one more definition is there. Impulse function is also the derivative of the step function. If we take the derivative of the unit step function, you will also get the delta function. The discrete time, this is the discrete time impulse function. Delta n is equal to 1 for n equal to 0 and 0 for n not equal to 0. Now, various signal manipulations of discrete time signals can be done. For example, if a signal is delayed by k, which is an integer, right? If k is greater than 0, the time shift results in a delay of the signal by k samples. But if k is less than 0, the time shift results in an advance of the signal by k samples. This is, let's say, xn, and how we can get xn minus 2. The signal will shift towards right by 2 samples, and if for xn plus 1, because k will become minus 1, and the signal will shift towards the left, right, for 1 unit of time. So this signal, this value has come here, and the 0 has gone further. So the whole whole discrete sequence has shifted by 1 unit of time towards left. Here the whole discrete sequence was shifted by 2 units of by 2 sample numbers towards right. What is a discrete system? A discrete time system is a device or algorithm that operates on a discrete time signal called the input or excitation according to some well-defined rule to produce another discrete time signal called the output or the response. So input is also known as the excitation pulse or excitation of the system, that how the system is excited, with what kind of pulse it is excited, and the output will be called as the response or the output of the system. And the relationship between the output and the input is defined by a parameter h. We call this h as the transfer function of the filter, right? So this is how h basically denotes the transformation or processing performed by the system on xn to produce yn. Now, how the systems can be represented using a block diagram? The various components which are used to represent the system are as follows. We will take the case of first component, which is an adder, a system that performs the addition of two signal sequences to form another sequence, which we denote as yn. And this is a memoryless component of the block diagram, uh, right? So if x1 and x2 n are two discrete sequences, so this is the adder symbol, and this symbol will be used to show the summation of these two discrete sequences to get yn. All right. Rest of the things are self clear, because this, if this is the sequence, this is another sequence. So the final sequence will be the addition of these two. 4 minus 2 is 2 here, 5 plus 4 is 9, minus 3 plus 3 will be 0. All right. A constant. Now another important entity in the block diagram is a scalar. If the input, if, let's say if xn is the input and it is to be multiplied by a scaling factor a, then this symbol will be used, and at the output we will get a of xn. The other component is the unit delay element. The unit delay element is a special system that simply delays the signal passing through it by one sample. And for example, if xn is passed through the unit delay element, the output will be xn minus 1. And it is thus the basic building block. This building block requires memory, because it has to get the input, the delayed version of the input also, right? So it has to store that value. So it is this component has memory in it. The use of symbol z to the power minus 1 to denote the unit of delay. So if xn is the input, yn will be xn minus 1. A discrete time system consisting of these adders, multipliers, and unit delays can always be described by a set of difference equations. The equations would be ordinary algebraic equations if no delays were present. For example, yn is equal to xn minus 2. So yn is basically xn minus 2. That means if xn is the input at the present time, we need two inputs going backwards by 2 units of time, right? If xn is the input, delayed by 1 will give us xn minus 1, delayed by another 1 unit of time will give us xn minus 2. Yn is equal to xn plus 0.25 yn minus 1. So this is how the in the previous example, you see there is no feedback path. No feedback path is there which is coming from output towards the input. It is only the feed forward path. No feedback path is there. But in this equation, if you see, there is a feedback path also, because the output yn is being fed back towards the input with a delay of z minus with a 1 unit delay. So at the output of this delay will be yn minus 1, and will then be multiplied by a scaling factor of 0.25. That's how this equation can be represented using a block diagram. Similarly, this equation yn is equal to a going from 0 to 4 can be represented by this equation. and we can also draw the block diagram. Now let us look at this equation. Yn is equal to a0 xn plus a1 xn minus 1 minus b1 yn minus 1. So we will have to draw the system implementation for the above difference equation. So we say xn, we start from here, xn is the input. So first of all, it has to be multiplied with the scaling factor a naught. Then it is added with xn minus 1. So we put a delay element here and we also multiply it with a1. So at the output of this delay element will be xn minus 1, will then be multiplied by a1. So a1 xn minus 1, from this side a naught xn will come, that will form vn. This is the feed forward part of the overall system, and there is a feedback term also which feeds back the yn, which is the output, with a delayed, with 1 unit of delay, and is also multiplied by minus b1. So multiplied by minus b1, a naught xn plus a1 xn minus 1 coming from the feed forward path, and minus b yn minus 1 coming from the feedback path are added, and that forms the output, final output of the system. And this is known as the direct form 1 structure. This is known as the direct form 1 structure. Okay. Now if you see here, system 1, if I represent a system 1 with vn value, then this system 1 is actually a feed forward system. System 2 is represented by this portion of the overall system. This is a feedback system, right? Now if we say that xn is first passed through a feed forward system, then it is passed through a feedback system, and we get the output. But if we interchange the system, the feed forward and feedback path, feedback system, for example, if we bring system 1, system 2, which is the feedback part of this portion of the overall system at the beginning, and we take feed forward, which is system 1, at the we place it afterwards, after the feed forward path, feed forward part of the system, then this will be called as the direct form 2 structure. All right. And of course, these are cascaded because system 1 is cascaded with system 2 to give the final output. We will also see more in cascade structures. All right. Now this is the feedback path. We try to implement the system using this second this second portion of this block diagram. What we do, we try to solve this example. This is system 1, this is system 2. What we will do is we will place the system 2 here and system 1 here. Okay, so system 2 is placed here at the start, and system 1 we will bring here, and we can prove it that the overall output remains the same. There is no change in the output. This type of structure is known as direct form 2 structure. And if you see here, because in the feedback part there is a delay element, in the feed forward path there is a delay element, and they are attached to a common point. Now if why, that means we are using two delays unnecessarily. Can we combine these two delays? Yes, we can combine to reduce the number of overall delays. And if we combine the delay, number of delays in the structure of the system, then we call that form as the canonical forms implementation. So I have discussed three rather forms of the system structures. One is the direct form 1, direct form 2, and the canonical structure. We will come to the cascade and parallel structures afterwards. Okay, the same thing is said here. There is no need for two delay operations. Same thing is said. If you combine the two delays, we can solve the same difference equation and represent the same difference equation using this block diagram, where only one delay element will be sufficient, and this type of structure will be called as the canonical structure. And we can prove this also, that the implementation has the same output in both the cases. There is no change in the output. So the proof is also given. Yn is equal to, in this case, Yn is equal to a naught xn plus a1 xn minus 1. Now if we take Pn here, we get Pn. So we Pn is equal to xn minus b1. So here Pn is there, Pn will be delayed and multiplied by minus b1. So this is our 2.3 equation. And what will be yn? Yn will be Pn plus this the all the blocks will be considered, and we will form that yn is equal to a naught Pn. If you see here, this is a naught Pn is coming from this side, it will be a naught Pn, and Pn is also delayed, which gives me Pn minus 1 multiplied by a1. So coming from this side and coming from this side, both will be added to produce the yn. So this is my yn. Now I will substitute n to n minus 1 in equation 2.4. I get this equation. Multiplying equation 2.5 by minus b1, I will get this equation. This is only adding equation 2.4 and 2.6 will give me the same equation as the uh, as is coming in both the type of structures, minus b1, right? Okay. So let us, this proof is actually for the direct form 1 and direct form 2. It will prove that the two structures direct form 1 and direct form 2 will remain the same. This is my direct form 2. All right. Let me come back to the point so that it will. This is my direct form 1 structure of the field of the same system that I tried to explain. So this is the difference equation for the direct form 1. Now, as I said that we can put it in the direct form 2 structure also, meaning by I can put system, I can put the feedback system first and then the feed forward system. If I do that this manipulation, then I will say that the output will remain the same. That's what I am trying to prove here. This is my direct form 1 equation, difference equation. Now I start with direct form 2 implementation. I write the equations and I prove that the final difference equation is the same as the direct form 1 structure, right? So direct form 1 and direct form 2 are anonymous to each other, and canonical structure is basically for the saving of the hardware, where if in this example, if two delay elements are being used, we can do the job in one delay element even, and this can be applied to larger systems also, and this will reduce the number of resources required to implement the system. Okay, let us now discuss about the classification of discrete time systems. Right, in the classification of discrete time systems, we have already you must have studied in your signals and systems course also, where the general categories of the systems can be static systems or dynamic systems, time invariant or time variant systems, then linear systems and nonlinear systems, causal systems, stable systems, and unstable systems. So we will, I stop my lecture here. We will cover this part in the coming lecture. Thank you.